In this video, I will show you how to do some optimization problems. That's where you try to find the inputs that will give you the best outcome, like the maximum volume or the minimum cost. Example 1. You want to enclose a garden with fencing to keep the rabbits away. A shed will serve as the boundary for one side of the garden, and fencing is needed for the other 3 sides. If you have 60 feet of fencing, what is the area of the largest garden you can enclose? Let's start by drawing a simple diagram. So here's the shed, and here are the 3 sides of fencing with dimensions x and y. We are told that we have 60 feet of fencing to use, and I see that we have 2 y lengths and 1 x length. So that should give us a total of 60. In other words, x plus 2y should equal 60. This is the secondary relationship, which we will need later. The primary relationship is whatever we are trying to optimize. In this case, we are trying to maximize the area. Of course, the area of this garden is just x times y, so this is the primary relationship. We need to rewrite this in terms of a single variable. This is where the secondary relationship comes in. Let's get one of these variables by itself and do a substitution. Subtracting 2y from both sides, we get x is equal to 60 minus 2y. Let's substitute this expression in for x right here. So area equals 60 minus 2y times y. Distributing the y, we get area is equal to 60y minus 2y squared. Finding the largest area means finding the absolute maximum area. So our strategy will be to make a candidates test for the area. The first step of making a candidates test is to find the critical values of area. The critical values come from the derivative. So let's see, a prime will equal 60 minus 4y. The critical values will occur when a prime is equal to 0. So we have 60 minus 4y is equal to 0. Adding 4y to both sides, we have 4y is equal to 60. Dividing both sides by 4 gives us y equals 15. So this is the only critical value. Now it's time to set up the candidates test using the endpoints for y and the critical value that we just found. The lower limit of y is 0. No length is smaller than 0. And then we have the critical value of 15 in the middle. The upper limit for y is 60 because we have a total length of 60 feet of fencing to use. Of course, if y is 0, that makes the area 0. What about when y is 15? Using this version of the area formula, we have 60 times 15 minus 2 times 15 squared. That turns out to be an area of 450 square feet. When y is 60, you get an area of negative 3,600 square feet. You can't actually have a negative area, so this is not the answer. So the maximum area is 450 square feet. In summary, we say the garden will have a maximum area of 450 square feet. See candidates test. Example 2. We want to construct a box whose base is a square that has a volume of 36 cubic feet. The material used to build the top and bottom cost $8 per square foot, and the material used to build the sides cost $6 per square foot. Determine the dimensions that will minimize the cost to build the box. First of all, here's my sketch of the box. We are told that the base of the box needs to be a square, so I've labeled the dimensions as x by x, and then the height of the box is y. We can get the secondary relationship from this statement right here. the volume has to be 36 cubic feet. We know that the volume of a box is length times width times height. So that is x times y. In other words, the volume will equal x squared y. Our primary equation will come from the thing that we need to optimize. In this case, we need to minimize the cost to build the box. Let's let C represent the cost to build the box, and we need to set up an expression for this cost. We are told that the top and the bottom cost $8 per square foot. So the cost of the top and the bottom of this box will be $8 times the total area for the top and the bottom. Since the top and the bottom are both squares, the top and the bottom both have an area of x squared. Since there are two of them, then the total area will be 2x squared. So this is an expression for the cost of the top and the bottom of this box. Now we need to add on the cost of the sides. We are told that the sides cost $6 per square foot. So it's going to be $6 times the total area for all the sides. If you look at one side, like this side in the front, the area is x times y. But there are four sides. There's a front and a back, there's a left and a right. So that's 4xy. So this is an expression for the cost of all the sides. Taken together, we have this expression for the total cost of the box. Simplifying a tiny bit gives us this. Next, we need to rewrite this equation so that cost is in terms of a single variable. That's where the secondary equation comes in. We are told that the volume of the box must be 36 cubic feet. So x squared y equals 36. Dividing both sides by x squared gives us y equals 36 over x squared. Let's substitute this expression in for y. So now we have this. On the next step, we will cancel out one of these x's, and we will multiply 24 times 36. So now we have this. In a minute, we need to find the critical values, which means I'm going to need the derivative. To find the derivative, it will be easier if I rewrite this as 864 x to the negative 1 power. Taking the derivative term by term gives us c prime equals 32x minus 864 x to the negative 2 power. That last term is the same as 864 over x squared. We need to find the critical values by setting c prime equal to 0. So we start off with 32x minus 864 over x squared equals 0. In order to get rid of this denominator, let's multiply both sides of the equation by x squared. Then we will have 32x cubed minus 864 is equal to 0. Adding 864 to both sides gives us 32x cubed is equal to 864. Dividing both sides by 32, and we have x cubed is equal to 27. Taking the cube root of both sides, we have x is equal to 3. This is our only critical value, so we can use it to make the candidates test. The lower extreme for the value of x is 0, but x cannot actually equal 0 because that would mean we had no box. So I'm just going to put NA on that. Then we have the critical value we just found in the middle. What about the upper limit for x? Remember that the volume has to be 36. So the maximum reasonable value for x would be 6, because that would give us 6 times 6, which is 36, without even involving y. We would already have our 36. So that's the biggest reasonable value for x. So there you go. To find the cost when x is 3, we will substitute 3 in for x in this expression right here. When x is 3, the cost turns out to be $432. Similarly, when x is 6, the cost turns out to be $720. We want to minimize the cost of the box, so we will let x equal 3. Let's find the y value that goes with it. At the beginning of the problem, we found that y is equal to 36 over x squared. So when x is 3, y equals 36 over 3 squared. In other words, y equals 36 divided by 9, which equals 4. In summary, the dimensions of the box that minimize the cost are 3 by 3 by 4. See Candidates Test. Example 3 is calculator active. The equation y equals x squared plus 3x minus 5 represents a parabola. Name the point on the parabola that is closest to the origin. Let's start by graphing this parabola to see what we've got. So go to y equals, type it in, and hit zoom 6. Here is the graph of the parabola, and we are trying to find the point xy that is as close as possible to the origin. As I am sure you recall, this is the formula for the distance between 2 points x1, y1 and x2, y2. But if the first point is the origin and the second point is xy, the distance formula simplifies to this. In other words, the distance between a point xy and the origin is given by the square root of x squared plus y squared. Finding the point closest to the origin means minimizing this distance. So this is our primary equation. We need to rewrite this so that we only have one variable. Luckily, they gave us the secondary equation, y equals x squared plus 3x minus 5. So let's substitute this expression for y. To find the absolute minimum value of distance, we would normally find the critical values by finding d prime. This is going to turn out to be the long way, but we could do it. We have this expression all raised to the 1/2 power. So d prime would be 1/2 times x squared plus 3x minus 5 squared to the negative 1/2 power. But then the chain rule demands that we now multiply by the derivative of the inner function. So the derivative term by term will be 2x. We have some more chain rule happening on the next term. So the 2 comes out to the front. And so we're going to leave that x squared plus 3x minus 5. And but then we have to multiply by the derivative of this inner function. So we will now multiply by 2x plus 3. All of this is d prime. Did I mention this was the long way? The shortcut is to make a new expression which I will call I, because it will simply be the inside of what we have for distance. So x squared plus 3x minus 5 squared. If we can find the value of x that makes the inner expression as small as it can be, that same value of x will make the distance expression be as small as it can be. So forget about d. Let's just find the absolute minimum of I. And to do that, we need to find I prime and then find the critical values. So for the first term, we have 2x. Now a little bit of chain rule. The 2 comes out to the front, so we have 2 times x squared plus 3x minus 5. And now we multiply by the derivative of the inner function. So we multiply by 2x plus 3. So this is I prime. The critical values will be the values of x that cause I prime to equal 0. And here's where we are glad that this problem is calculator active. Let's type this expression for I prime into the calculator and see where it equals 0. So here I've typed I prime in as y2. Let's hit zoom 6 and take a look. I want to modify the window a bit so I can see more of the top and bottom of this graph. So hit window. Let's let y min be, let's say, -30. And let's let y max be +30. And hit graph. Remember, this is a graph of I prime, and we need to find these three places where I prime is equal to 0. I'm going to show you two different ways to do that. For the first method, hit second trace and choose 0. So option number 2. Let's go for this first x-intercept right here. It's asking for left bound, so we need to hit the left arrow key until we get somewhere to the left of this first intersection point. So anywhere over here is fine. Hit enter. Now it asks for a right bound, so hit the right arrow key until you go past that intersection point and hit enter. Now it says guess. Just move as close as you can get to the intersection point and hit enter. So this is the first critical value. Let's store this into a letter on the calculator. So let's quit our way out of this by hitting second quit. Hit the X button and then the store button. And I'm going to store this into letter A. Also record this into your work. So -4.041. I'm also making a note to myself that I stored this in letter A. I'm going to show you how to find the next critical value using a slightly different method. So go back to y equals. For this method, we need to graph the x-axis itself. So I'm going to put y1 equals 0. So just hit graph, and you can see that the x-axis is now graphed in blue. Now I want to find this middle intersection point. Instead of hitting second trace 0, this time we will use option 5 for intersect. Many students prefer this method because you don't have to do the whole left bound, right bound thing. You can just come very close to the intersection point and hit enter, enter, enter. So here is the second critical value. Let's store this into letter B. So second quit, X, store, alpha B. Let's also record this in our work. X equals -1.611. I'm going to stick with the same method for the third critical value. So just hit graph and do second trace 5. Move the pointer close to the third critical value and just hit enter, enter, enter. So there it is. Let's store this into letter C. So we hit second quit and X store alpha C. In your work, write X equals 1.152. Now that we have our critical values, I would love to make a candidates test. But there is a problem. For a candidates test, we need to include the endpoints, the lower boundary and the upper boundary of these x values. But guess what? There is no lower boundary, there is no upper boundary. There's nothing stopping us from going to the left forever and going to the right forever. In this case, it will turn out to be okay because these extreme values were not going to be the answer anyway. We are trying to find the point that is closest to the origin. And as we go to the left forever, we are getting further and further away from the origin. Similarly, as we go to the right forever, we are just getting farther and farther away from the origin. So those weren't going to be the answers anyway. So let's make our candidates test using the three critical values that we have. and in the summary, we will mention why the endpoints were excluded. Let's use the graphing calculator to help us find the distance at each of these three x values. We will need to type this expression for distance in as y3. So here I have typed the distance expression in as y3. In order to easily evaluate this distance at the three critical values, I want you to change one setting on your calculator. Hit second window to access the table setup menu. Change where it says independent from auto to ask. All right, so make yours look like mine. Now hit second graph to access the table menu. Notice that we have y3 in the third column. We can type any value we want for x, and the value of y3, in other words the distance, will show in the third column. We want to evaluate that distance at the three critical values, these three values right here. Remember that we have these stored in as A, B, and C. So we can simply type alpha A, alpha B, and alpha C. So these are the three distances that correspond to these three critical values. So the minimum distance occurs when x is 1.152. We just need to find the y value that goes with it. Remember that y equals x squared plus 3x minus 5. So we just need to substitute 1.152 in for x. Better yet, on the calculator, we can just substitute c in for x. So we need c squared plus 3c minus 5. So alpha c, so we have c squared plus 3c minus 5. Negative 0.217. In my summary, I'm going to start with this statement that explains why endpoints were not included in the candidates test. As x approaches positive or negative infinity, the distance increases without bound. The point on the parabola closest to the origin is 1.152, negative 0.217. See Candidates Test. Example 4. Oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume increases at a constant rate of 2,000 cubic centimeters per minute. A recovery device arrives on the scene and begins removing oil. The rate at which oil is removed is R of t equals 400 square root of t cubic centimeters per minute, where t is the time in minutes since the device began working. Find the time t when the oil slick reaches its maximum volume. Justify your answer. Normally, when they ask us to find the time of the absolute maximum volume, we start with an equation for volume. Then we find the derivative. So we can find the critical values, where v prime is equal to 0, so we can make a candidates test. But in this case, we are not given an expression for volume. So what do? The thing is, we don't actually need an expression for volume because they gave us enough information to go directly to v prime. The overall rate of change of the volume of this oil slick is going to equal the rate in minus the rate out. Before the recovery device arrived on the scene, the volume of the oil slick increases at a constant rate of 2,000 cubic centimeters per minute, so that is the rate in. The device removes oil at a rate of 400 radical T cubic centimeters per minute, so that is the rate out. So this is the equation for the overall rate of change of the volume of this oil slick. The critical values of volume will be where v prime is equal to 0. In other words, where is 2000 minus 400 radical T equal to 0? adding 400 radical t to both sides, we get 400 radical t is equal to 2000. Dividing both sides by 400, we get radical t is equal to 5. And squaring both sides, we get t is equal to 25. Normally, the next step would be to use a candidates test to find the time when the oil slick reaches its absolute maximum volume. But there are two problems with that. For a candidates test, you need endpoints on the time. The lower limit for time would be 0. But in this problem, we are given no upper limit for time. The time just sort of goes on and on. The other problem is to evaluate the volume at these the critical values or the endpoints. We need an expression for volume, which we don't have. So what do? Here's a useful fact to keep in mind. When there's only one critical value, a relative max is also the absolute max. So that's the case that we have here. So we just need to prove that this is a relative max, and we can conclude that it is also the absolute max. We can use a V' sign chart to see if the volume of the oil slick has a relative max at t equals 25 minutes. Remember, V' equals 0 at t equals 25. This expression will be positive for values of t between 0 and 25. For values of t that are greater than 25, you are now subtracting a value bigger than 2000, so you get a negative number. Notice that V' changes from positive to negative. That means that the volume goes from increasing to decreasing. So we do have a relative max at t equals 25. In summary, the volume of the oil spill has a relative max at t equals 25 minutes because V' changes from positive to negative. Since t equals 25 minutes is the only critical value, this relative max is also the absolute max.